Okay, I don't have your test back ready yet. Maybe Wednesday, we'll see. Before the test, we were doing circular motion. Um, and I divided things up into two types of problems. Basically, you have to decide when you look at a problem, is it tetherball? Or not? I mean, that's just all. So there's this one kind of problem that looks like a tetherball game, and we'll talk about that next. But you just have to decide whether it's that. If it is, you're going to use one approach. Everything else, we're going to use a different approach. And for the other stuff, if it's not a tetherball problem, I gave a set of steps. And so I'm going to do one more example problem of that type, just sort of remind you of the approach. So let's think of one where you're swinging a mass around on a string like this, and down is this way, so that means the thing is lower, closer to the ground when it's at the bottom of this circle than when it's at the top. So that matters because it has to do with how gravity affects things. And let's say that the mass of this ball is 60 grams, so 0.06 kilograms. And let's say that the length of the string is 0.2 meters. And let's start by thinking about when the mass is exactly at the side right there. Let's call that point P. And let's say that at P, the ball has a speed of 5 meters per second. And we want to calculate, let's say we're given that it's slowing down at that instant. It's on the way up. So it's going around the circle that way. And so it's slowing down when it gets to P at a rate of 9.81 meters per second squared. And then we'll come back and do a couple of other cases, but let's do this one first. So what we want to calculate is the tension in the string. Okay, so the first step is always to make sure that you're viewing this problem in the right plane, that you're looking at it in the plane where you can see the circle. In this picture, we are, so we can draw the circular path like that. And the point we're looking at is here. And I'm just going to draw the coordinate system. I'll put it centered at the middle. Where you put the origin doesn't matter in these. That's just the orientation I'm going to use. And I'm going to draw the velocity vector. So it's that way. And I'm going to draw the tangential acceleration based on whether it's speeding up or slowing down. Is this speeding up or slowing down? Slowing down. So the tangential acceleration is opposite the velocity. The centripetal acceleration is always toward the center. And now we can start to calculate some of these magnitudes. Okay, so the centripetal acceleration magnitude is the speed squared divided by the radius of the circle. What's the speed? 5. So we have 5 squared. And what's the radius of the circle? 0.2. It's the length of that string. And so this is 125 meters per second squared. Now that we have the magnitude, we can put that into vector components. Question?
Will we be given that problem too, or is that a good memorizing one?
This formula, the v squared over r, yes, that'll be given, yes.
Okay, awesome, thank you.
Is this centripetal acceleration, you can see it's parallel to the x-axis. Is it positive or negative x component? Negative, so the centripetal acceleration vector is negative 125, 0. And now let's figure out the tangential acceleration. Do you always have a tangential acceleration in circular motion? No, if the speed is constant, you don't. Okay, this one, we're told that the speed is changing. We're told by how much. So this one definitely has one. You can see that this is parallel to the y-axis. Is it in the direction of positive or negative y? Negative, so the tangential acceleration is 0, negative 9.81. So the total acceleration is the sum of these two parts. And so that's negative 125, negative 9.81. So you can think of that as kind of like always the first part of this problem. Figure out everything you can figure out about the acceleration. Usually, almost always, you can calculate the full acceleration vector. Now we're going to go to the Newton's second law stuff. So we're going to do a free body diagram of the mass. So remember, for a free body diagram, you're drawing the weight force. That's acting down at 0.06 times 9.81, so that's 0.58, 58, what is that, 8, 5? .5886. And now the only other force, you go around the boundary and look for where the surroundings make contact. The only other contact is where the string touches it. It's at this point along the circular path So the string is going this direction and the force is away from the body. And I'll call that T. Okay? Any questions about that?
Would it be fine in our calculations for 0.59?
Yes. Sure. Yep. And so now Newton's second law, the T is in the negative X direction. So we have negative T 0 plus 0, negative 0.5886 is equal to the mass, 0.06, times the acceleration vector, negative 125, negative 9.81. And now we can use the X equation, and we get negative T is equal to negative 7.5. So the tension in that string is 7.5 newtons. Any questions about that calculation? Okay, let's do two more calculations. Let's calculate the tension in the string at the top of the circle and the bottom of the circle. Does anybody have any thoughts on where this tension is going to be the highest? Like, yeah, that's right. And I mean, if you picture using a really weak string as you do this and just imagine where you'd be worried about it flying out of your hand. It always would be at the bottom because that's where that string is supporting the most force. Okay, so let's do those calculations. I don't have that in my notes, so I actually have to bottom of the circle, the speed is 5.38 meters per second. So here's our circular path. We're at the bottom here. Our coordinate system is this. The velocity vector is this way. There's a constant speed at the bottom because the height isn't changing. So the tangential acceleration is 0. The centripetal acceleration is up toward the center. The magnitude of the centripetal acceleration is v squared over r. So that is 5.38 squared over 0.2. So that's 144.62 meters per second squared. This is just the magnitude, not the vector. To put it into the vector, that's in the positive y direction. So the centripetal acceleration vector is 0, 144.62. And then the total acceleration is the sum of the two parts, but the tangential is 0. So we get a total acceleration of 0, positive 144.62. And now the free body diagram. The weight is down. That's 0.5886 newtons. The cable tension acts up. And so now Newton's second law says 0t plus 0 negative 0.5886 is equal to the mass times the acceleration vector and so T is equal to 9.27 newtons. So at the middle height, the tension is in the middle. At the top, you have the lowest tension, and at the bottom, you have the highest tension. Anybody in here ever do gymnastics? Remember, the spectacular bar wipeouts in men's and women's gymnastics always happen as people are swinging through the bottom of the, and this is the reason. So if there's any problem with your grip on the bar or anything, the bottom point of that circular motion is where that's going to be exposed, you know? Anybody have any questions about any of those? Yes.
What did we say, like, the weight of the ball was? Like, where did we get
The mass-
0.588?
The mass is 0.06, so the weight is 0.06 times 9.81. That's just the mass of like a pinball, like a metal pinball. Yep.
How did you find the speed for each of them?
Okay, so for now, I want those to just be given, but I will, when we start talking about energy, I'll tell you how I did that. But so far, we don't know how to do that. Any other questions? Okay, so I said that we're dividing everything up into tetherball and not tetherball. So let's think about these tetherball problems now. These are actually simple calculations. The only reason that I separate them out is because there's a very easy approach for this kind of problem that doesn't work for other kinds of problems. Okay, tetherball problems. In order to be a tetherball problem, well, it's a case where this thing is moving in a circular path like this. The rules are, first, the only contact is a cable. And second, the circular path has to be parallel to the ground. Okay, so for example, a case like this, where this ball is swinging around a pole. Well, that actually is tetherball, so that's clearly a tetherball problem. This one, we can use this approach. That's supposed to be a check mark, not a V. But here are two that might seem like they would work at first, but they don't. The first one is, imagine you have a ball on a string and it's moving along the ground in a circular motion, like rolling or sliding along the ground. Okay, this one is not a tetherball problem because the only contact isn't the string. There's contact with the cable, but there's also contact with the ground. Okay. Another one that doesn't work is the one we just did. Where gravity acts this way. That one doesn't work because the circular path isn't parallel to the ground. Okay. And one important fact about tetherball problems, and really this is the thing that makes this technique possible for this, is that tetherball problems are always uniform circular motion. Uniform circular motion. In other words, the tangential acceleration is always equal to 0. So we don't have to worry about that. We don't have to think about calculating it or anything. And so once you've identified a tetherball problem, here's a set of general steps for doing it. First, take a side view. So this is really where this differs from the other approach for other problems. In all the other problems, we take a view where we can see the circular path as a circle. In this case, we're looking from the side, so the circular path from our view is just kind of looks like it's going back and forth, okay? So it would look like, so there's the view we're gonna take, and the circular path is here, okay? And I'm gonna draw my coordinate system like this. The second step is to draw the centripetal acceleration. Toward the center of the circular path. So our centripetal acceleration goes this way. Third, we're going to calculate the magnitude of the centripetal acceleration using v squared over r. And that the radius of this circle now is not the length of the string, because, so if I draw this Okay, so our centripetal acceleration is going this way. The radius of the circle is this, okay? And that's not the length of this cable. The length of this cable is L. If you know this angle theta that the string makes with the horizontal, then the radius of the circle is L times the cosine of theta. Okay? Do you see how that works? This is a right triangle. And so if you know that theta and you know that L, then you know the radius of this circle. Okay, and now, you know, you go on to free body diagram and Newton's second law. And Newton's second law we're usually going to use to calculate the speed and the cable tension. Okay, so let's go through an example problem. Let's say that this string makes an angle of 45 degrees with the horizontal. Let's say the length of the string is 0.25 meters. The mass is 0.1 kilograms. And we want to calculate the speed and the cable tension. So before I go into this, just to have like your intuition right, does it sort of make sense that that angle is determined by how fast this is going? So even though like I haven't given you the speed, the fact that I've given you that angle that's why it's going to be enough information to determine the rest of the stuff. The faster you spin this thing around, the smaller that angle gets, the closer it gets to horizontal. Okay, it never can be horizontal. You know, that would take infinite speed, but it just keeps getting closer to it. Okay, so we're going to take a side view just like it's drawn. And I'm going to use a coordinate system like this. The centripetal acceleration goes toward the center of the circle like this. The magnitude of the centripetal acceleration is v squared over r, and r is 0.25 times the cosine of 45 degrees. And so we don't know what that v is yet. We're going to calculate that in the end. So for now, I'm just going to leave it as v squared divided by some number or multiplied by some number. So you can write this as v squared over 0.177. All right, well, that centripetal acceleration is in the positive x direction. So This is equal to v squared over 0.177 and then 0y. The total acceleration is the tangential plus the centripetal, but our tangential is 0. So we just get v squared over 0.1770. And now Newton's second law, free body diagram first. So here's the body. There's a weight force acting down. The mass was 0.1, so 0.1 times 9.81 is 0.91981. The only thing contacting the boundary is the cable. And so that pulling force is parallel to the cable away from the body. And I'll give that the value T. Now Newton's second law, to come up with the components of that vector, this is going to be T times the cosine of 45, T times the sine of 45. The weight force is 0, negative 0.981. And that's equal to the mass of 0.1 times the acceleration that we just figured out, v squared over 0.177, 0 for y. And now we have these two equations. The x equation says cosine of 45 is 0.707 times t is equal to 0.1 over 0.177 v squared. So we can't solve this equation by itself. It has two unknowns in it. But the y equation, we can. So that one says sine of 45 is 0.707. So this is 0.707 t minus 0.981 is equal to 0. And so from this y equation, we can calculate that t is equal to 1.39 newtons. And then we can plug that back into the x equation. So 0.707 times 1.39 is equal to 0.1 over 0.177 v squared. So v squared is 1.736. Take the square root. And you get 1.32 meters per second. And you have to choose which one of these you want, but this is a speed, so we want the positive. Speed is always positive.
Are you gonna give us like the speed and everything else and make us find the angle?
Find the angle. Yeah, good question. I was just going to mention that. you need to use inverse trig for that, and we haven't talked about that in this class, so no. This is really the only way that I'll do it. But if you're familiar with inverse trig, it's pretty easy to imagine how to do that. You just have a number here that you know, and then you go and back calculate the angle. Okay. I want to do one other kind of example. I'm not going to do another tetherball one because they're really exactly like that. If, you just have to do a couple to get familiar with it, and they all go exactly in that form. But here's a kind of problem that you see pretty often. So let's imagine that somebody's on a motorcycle going through a loop-de-loop. And I don't know what a motorcycle looks like. Yeah, exactly like that. Okay, so this guy's going this way. And let's say that this loop-de-loop is a circle with a radius of, how big could a loop-de-loop be in a circus or something? What do you think the radius or the diameter is? I'd say a 2-meter radius. Maybe that's possible. Depends on how fast. Okay, so let's say that this is 2 meters. And we want to know how fast does the motorcycle have to be going So how fast does it have to go at the top to stay on the track? So you can imagine if this thing was going over the top at 1 mile per hour, the motorcycle would just fall off the ramp. It wouldn't be going fast enough to stay on there. And so there's kind of one idea that we need to use in order to figure this out. And that is when we draw a free body diagram of the motorcycle at the top, the ground is going to be pushing down, right? If we calculate that pushing force from it's going to be pushing down, but if we calculate that pushing force from the track, it has to be pushing down. If it switches to pulling up, that's when tracks can't do that, so that guy falls off of that circular path. Okay, so our cutoff point is going to be exactly when that normal force from the track is 0. Okay, so the cutoff speed is going to be when the normal force from the track is 0. Okay, is this a tetherball problem? No, so that means we want to take a view where we see the circular path. And the point we care about is here. Oh, and we need a mass for the person in the motorcycle. I guess really it won't matter, but let's give one. Let's say that the mass is 200 kilograms. Okay, the velocity at this instant would be this way. We'll assume that there's no tangential acceleration. That's a reasonable assumption, although you could make it so it was changing speeds up there. So let's just assume that the tangential acceleration is 0. That's something I'd have to tell you in the problem, you know. And the centripetal acceleration goes this way, down towards the center. The magnitude of the centripetal acceleration is v squared over r. R is 2 meters. That's the radius of this circle. And we're trying to calculate that speed, so we can't put a value in yet. This centripetal acceleration is in the negative y direction. So as a vector, this is 0 for x, negative v squared over 2 for y. And the tangential acceleration, well, let's say the acceleration is the tangential plus the centripetal. The tangential is 0. And so the total acceleration is 0 for x, negative v squared over 2 for y. And now I'll go to the free body diagram. So this is the shape of an upside down motorcycle. Perfect. There's a weight force down of 200 times 9.81, so that's 1962. And then there's a pushing force from the surface onto the wheels, like this. I'll call that N. Okay. And Newton's second law. Well, now here's where our requirement comes in. So I said that our cutoff for where this would stay on the track is when that normal force is, whether that normal force is 0 or above, or whether it's negative. So I'm going to set this equal to 0.
Do you want us to write the normal force in the free body diagram?
I don't think I'd give you any problems like this anyways. I just sort of wanted you to see it. But yeah, I think it's better if you draw it in there just because it's clear to yourself, clear to whoever you're talking to. So then Newton's second law says 0, negative 1962. Plus 0, 0, that's the normal force, is equal to the mass times the acceleration 0, negative v squared over 2. And now you can use the y equation. It says negative 1962 is equal to negative 100 v squared so 19.62 is equal to v squared. So v is equal to the square root of that. Uh, 4.42 meters per second. We want the positive. So for a loop-de-loop with a radius of 2 meters, this thing at the top needs to be going at least, that's right around 10 miles per hour. If it's going any slower than 10 miles per hour, it'll fall off the track. Any questions about that? Okay, let's stop there for today. The next thing we're going to do is go into a new topic, which is conservation laws. And so we'll be talking about conservation of momentum and conservation of energy. Okay, that's all.